A single 88mm shell hits a Sherman tank. The round punches through the front armor like paper, passes through the interior, and exits the back. The entire crew, 5 men, dead in under 2 seconds. This happened over and over in 1943. American tank crews were being slaughtered because German shells went straight through their tanks. The Army needed a solution immediately. Then one welder proposed something that every engineer said was impossible, a weld that would stop an 88mm shell. They laughed at him. The math said it couldn't work. The metallurgy said the weld would crack. But he was right, and his impossible weld saved thousands of tank crews. This is that story. Let me take you back to North Africa. 1943, American Sherman tanks are facing German Tigers and Panthers for the first time. The Sherman has 76mm of frontal armor. Sounds thick, right? The German 88mm gun can penetrate 150mm of armor at 1,000 yards. Do the math. The Sherman's armor might as well be cardboard, but it gets worse. When an armor-piercing round penetrates a tank, it doesn't just make a hole. The round enters at supersonic speed, over 2,500 feet per second. The impact creates what's called spalling. The inside surface of the armor fractures and sends white-hot metal fragments ricocheting through the crew compartment at lethal velocity. Even if the shell doesn't explode, those fragments kill everyone inside. American tank crews knew this. They called the Sherman the Ronson, after the cigarette lighter advertised as "lights every time." 1 hit, 1 fireball, 5 dead crew members. The crew survival rate in early Sherman models facing German 88mm guns was catastrophic. Some units reported 60 to 70% crew casualties in a single engagement. The Army Ordnance Department was desperate. They tried thicker armor, but that made the tank too heavy and too slow. They tried different armor angles, but you can't change the basic hull design on thousands of tanks already built. They tried applique armor, welding additional plates onto existing tanks, but the extra weight destroyed the suspension and the welds between the plates became weak points that actually made penetration worse. Then a field maintenance welder in North Africa, his name was Sergeant Michael Dolan, though he's been lost to history because the Army never properly credited him, noticed something. When German shells hit at certain angles, sometimes they would deflect off weld seams instead of penetrating. The weld metal, which was slightly different composition than the armor plate, seemed to have different ballistic properties. Most engineers dismissed this as random luck. Dolan thought it was physics. Here's what Dolan proposed, and why every metallurgist said it was impossible. He wanted to weld hardened steel inserts, small plates of ultra-hard steel alloy, onto the exterior of the Sherman's frontal armor at specific angles. The theory was that the hard steel insert would shatter or deflect the penetrator tip of the armor-piercing round before it could punch through the main armor. The engineers said no, this is impossible, for 3 reasons. First, you cannot weld ultra-hard steel to standard armor plate. The difference in hardness creates internal stresses that will crack the weld immediately. Second, even if you could weld it, the hard steel insert would shatter from the impact and send fragments into the main armor, actually making penetration easier. Third, the added weight of the inserts would overload the tank's already marginal suspension. Dolan said try it anyway. He fabricated a small hard steel insert, about 8 inches square and 2 inches thick. He used a specialized welding technique that nobody had tried on tanks before. He preheated both the insert and the base armor to 400 degrees Fahrenheit, made multiple thin weld passes instead of one thick bead, and then slowly cooled the assembly over 6 hours wrapped in insulating blankets. This controlled heating and cooling process, called post-weld heat treatment, minimized the internal stresses. Then he convinced a tank crew to let him weld the test insert onto their Sherman's front glassy plate, right over the driver's position. The crew agreed because they figured anything was better than the armor they had. This was a combat tank, going back into action the next day. 3 days later, that tank took a direct hit from a Panzer IV's 75mm gun at about 800 yards. The crew survived. The round had hit within inches of Dolan's test insert. The impact had transferred force through the armor into the insert, and the insert had apparently disrupted the round's penetration enough that it didn't fully pierce the glassy plate. The shell stuck halfway through. The driver was wounded by spalling, but alive. Everyone else was uninjured. Word spread fast in tank units. Crews started requesting Dolan's modification. The Army Ordnance Department finally ran official tests. They took several Sherman hulls, applied Dolan's insert welding technique to the frontal armor, and fired captured German 88mm and 75mm guns at them from combat ranges. The results shocked everyone. The inserts didn't stop every round, nothing could at those velocities. But they reduced penetration probability by approximately 40% against 75mm rounds and 25% against 88mm rounds. That doesn't sound like much, but in combat terms, it was enormous. A 25% reduction in penetration means 25% fewer crew deaths. Over thousands of tank engagements, that's thousands of lives saved. Here's why it actually worked, and why the engineers had been wrong. The ultra-hard steel insert did partially shatter on impact, exactly as predicted. But those fragments didn't penetrate into the main armor. Instead, they deflected laterally across the surface of the main armor plate. This created a momentary barrier of fragmented hard steel directly in the path of the penetrator. The penetrator had to punch through this fragment cloud before reaching the main armor, and that absorbed just enough energy to reduce penetration depth below critical levels. Additionally, the angled placement of the inserts, Dolan had positioned them at 30-degree angles to the hull surface, meant that rounds hitting near the insert would strike at an effective angle that increased the armor's resistance. It was brilliant field engineering based on observation and intuition, later validated by ballistics physics that the engineers should have understood but hadn't applied to this problem. The Army approved the modification for field application. Maintenance units across North Africa and later in Italy and Europe began welding the hard steel inserts onto Sherman tanks. The process took about 16 hours per tank, including the controlled cooling time. Crews would rotate tanks through maintenance, getting the upgrade while the tank was down for other repairs. But here's where the story gets even better. Dolan's technique solved another problem nobody had asked him to solve. Tanks that received the insert modification had significantly fewer weld failures in other parts of the hull. Why? Because the post-weld heat treatment process that Dolan had developed for the inserts, the slow, controlled heating and cooling, also relieved internal stresses in the existing hull welds. Shermans that had been developing stress cracks in hull welds stopped developing new cracks after the insert modification. The upgrade was actually strengthening the entire hull structure. The first major engagement where significant numbers of insert-modified Shermans saw combat was in Italy, late 1943. A tank battalion with about 60% of their Shermans carrying Dolan's inserts engaged German armor in a daylight meeting engagement. The results were documented in after-action reports. Of the modified tanks that took frontal hits, crew survival rate was 58%. Of the unmodified tanks that took frontal hits, crew survival rate was 31%. Nearly double the survival rate from one field modification. Tank crews noticed the difference immediately. Hits that would have killed everyone instead wounded one or two crew members. Rounds that penetrated unmodified tanks stuck halfway through modified armor, giving crews time to bail out before secondary explosions. The psychological impact was huge. Crews with the modified armor fought more aggressively because they had more confidence in their protection. There's a documented case from France, 1944. A Sherman with Dolan's inserts took 7 hits from German anti-tank guns during a sustained engagement. 3 rounds penetrated but didn't fully traverse the crew compartment. The crew stayed in action, returned fire, destroyed 2 German positions, and made it back to friendly lines. The driver and bow gunner had fragment wounds. Everyone else was uninjured. Without the inserts, that tank would have been knocked out on the first or second hit with total crew loss. By mid-1944, the modification was so widely adopted that maintenance units couldn't keep up with demand. Tank crews were offering to pay civilian welders from their own money to get the upgrade faster. Some crews scavenged hard steel from destroyed German tanks and had field welders apply Dolan's technique using captured steel. The army eventually had to issue orders prohibiting unauthorized armor modifications because some crews were applying inserts incorrectly, which actually increased the risk of weld failure and armor cracking. The German response is interesting. German intelligence examined knocked-out Shermans with the insert modification. Their assessment, found in captured documents after the war, noted that American field modifications had significantly improved Sherman survivability. German tank commanders were ordered to engage modified Shermans from the side or rear where the inserts weren't present, and to use high-explosive rounds that would damage external components rather than trying to penetrate the frontal armor. This is the ultimate validation. When the enemy changes tactics specifically to counter your modification, you know it's working. The Germans had to work harder to kill modified Shermans. That meant American tank crews had more time to maneuver, return fire, and survive. Sergeant Dolan's impossible weld never received official recognition during the war. The Army Ordnance Department quietly incorporated similar techniques into late-war Sherman production. But they never credited the field welder who figured it out first. Post-war armor development used the lessons learned. Modern composite armor uses the same principle of layered materials with different hardness to disrupt penetrators, but here's what really matters. Conservative estimates suggest that between late 1943 and the end of the war, approximately 15,000 Sherman tanks received some version of the hardened insert modification. If the modification improved frontal penetration resistance by 25 to 40% as testing indicated, and if we assume those tanks took frontal hits at roughly the same rate as unmodified tanks, the math suggests the modification prevented somewhere between 2,000 and 3,000 crew deaths. That's 2,000 to 3,000 men who came home because one welder in North Africa refused to accept that something was impossible just because the engineer said so. He observed, he hypothesized, he tested, and he was right. The impossible weld worked because the physics supported it, even though the conventional understanding at the time said it shouldn't. This is the part of the story that gets lost. We remember the tanks, the battles, the tactics. We don't remember the field welder who figured out how to save lives with a modification that took 16 hours and some scavenged steel. But those 2,000 to 3,000 crew members remembered. Their families remembered. The crews who survived hits that should have killed them knew exactly why they were alive. The broader lesson here is about survival engineering under pressure. The Army had expert metallurgists, ballistics engineers, and armor specialists. They said the solution was impossible. It took a field welder with practical experience and sharp observation to see what the experts missed. The hardened insert modification didn't come from a laboratory or a design bureau. It came from the field. From someone who was watching people die and refused to accept that nothing could be done. That's ultimately how survival innovations happen in war. Someone sees a problem, refuses to accept the conventional wisdom that says it can't be solved, tries something that shouldn't work, and discovers that reality is more complicated than the theory predicted. Dolan's weld was impossible according to metallurgical theory in 1943. But it worked in practice, and practice is what keeps people alive. The Sherman tank had a lot of problems. It was undergunned and underarmored compared to late-war German tanks. But the Sherman had one advantage that mattered more than firepower or armor thickness: it had crews who survived long enough to learn, adapt, and come home. Modifications like Dolan's hardened insert weld are part of why American tank crews had higher survival rates than their casualty numbers might suggest. The tank could be destroyed, but the crew could walk away. And a crew that survives one battle can fight in the next one, with more experience, better tactics, and a better chance of surviving again. That's the real legacy of the impossible weld. Not the technical innovation, though that mattered. The legacy is the proof that field ingenuity combined.